Alright, welcome back to Gabversity, where facts care not about your feelings. It is great to see you all. I thought I would introduce you to a bit of a view first. It's a lovely smoky day for some reason. With James Joseph, we have the whole crowd. And here we are. So, we are saying hello. We have True Faith, James Joseph, Paint Something. A big shout out to Paint Something, by the way, who's unlocked some videos on Gabflix. Got our good friend George. Got them all back. Alright, so in our last scope, we talked about Kirchhoff's laws of radiation. We spoke about stellar spectroscopy and how that can be used to determine the fingerprint of a star. Miss Bombshell, hey, Abyss, everyone is back. Hope you've all had some sleep. Gabversity from James Joseph. Alrighty, and we spoke about Wien's displacement law, and that was allowed us to figure out the temperature. Hello again. Ms. Bombshell, another one of our GoFundMe fans. I'm waiting on on my lawyer to get back to me about people investing in this book, which will be really exciting. Very excited about that. All right, Dario Ross. So the two laws of blackbody radiation that we spoke about, one of them was Wien's displacement law, or Wien. I don't like Wien because it sounds like a wiener, L. Brooks. So I call it Wien's displacement law. And basically all they say is that, hey, Paint Something. Congratulations to Paint Something with unlocking videos on Gabflix. Well done. The displacement law is that the wavelength, or the max wavelength, with respect to the blackbody spectrum shifts. Okay? In other words, when the temperature increases, we have a shift in the blackbody radiation. Hello. Why is that important? Well, that's one of the characteristics of the fingerprint. This allows us as humans, through astronomy, to discover what makes up a star. What are the outer gas layers of a star? What are the inner gas layers? What are the metallic layers? Which is quite amazing. On a side note, there's a special type of star called the magnetar. I think it's called the Magnetar. I call it Magnetar because it sounds more gangster, like X-Men. Magnetar. I am Magnetar. Anyway, these stars last only 10,000 years, which is nothing compared to a star. You know, the average star lasts around 5 billion or 10 billion years. It lasts 10,000 years. And it is so magnetic, right, that from halfway from the moon, it could wipe out your credit card details. That is how magnetic this thing is. It is just insane. In fact, like, you couldn't even get close because the ephemeral stars. Hey. Yeah, absolutely. And they could rip away, you know, the electromagnetic fields inside the own atoms inside your skin. It would rip them to pieces. It's just insane, these things that exist. My balance is negative. That is awesome. Too funny. You'll have to make a trip, man, to the star. Come back. That was the best joke of the lecture so far. All right. Two laws of blackbody radiation. That was the first one, right? And the law is this. You can write it down if you want. It's 2.9 by 10 to the 6 nanometers divided by the temperature in Kelvin. And we spoke about this last time. Kelvin is the scale that runs linear to Celsius, right? It's a 1-to-1 with Celsius. Do fast spinning neutrons don't they? Rip you apart? Yeah, they definitely rip you apart. But they all like to rip you apart in their own different way. The hotter the object is, the more energy it emits, and that's the flux. All right. So the flux is what we said was the energy per unit surface area, right? So if you have a flat table, it's the energy that runs, you could say, perpendicular to the table, right? Like having a stove, the heat coming off a stove, in a way, that would be flux, right? And it's what's interesting in astronomy, in physics, in all other sort of forms of physics, and in chemistry, is you find these constants. Now, they are embedded, these constants, in the universe itself. And that I find absolutely fascinating, right? And so some people argue, some people like to argue that's because God made it that way. Some say because there's multiple, infinite amount of universes. Obviously, we're not here to talk about that in Gabversity. But here, right, I'm going to show you, number one, the constant here, 2.9 by 10 to the 6. Okay, I don't know if you can actually let me turn it around the other way so you can see what I'm talking about. All right. So there, 2.9 by 10 to the 6 nanometers. All right, that's 1,000th of a meter. And a meter is what, like about 3.3 feet? So it's 1,000th of 3.3 feet, right? Divided by the temperature in Kelvin. And Kelvin, basically, 0 is absolute. 0, which is like 273.25 something negative Celsius, roughly, or negative 500 Fahrenheit or something. I can't remember exactly. All right, and the other constant is this one. This one here is the Stefan-Boltzmann Constant. Okay, and the relationship from energy to temperature to the power of 4 is via this constant. Yeah, Boltzmann, another genius who was falsely accused of shit and hung himself in the end. Turns out he was one of the world's geniuses. Okay, so the spectra of stars are more complicated than pure blackbody spectra we spoke about last lecture. And we spoke about how a continuous spectrum is released from something that's emitting light, okay? And then because of the gas around it, yeah, you concur, absolutely. Because of the gas around the stars, whether it's the outer layer of the star or whether it's a gas in a nebula, right, that absorbs certain lights or certain wavelengths of electromagnetic radiation, and it leaves only the remainder. And so you can work out, once again, that's another part of the fingerprint, because a combination of all of these, right, leaves you with a unique fingerprint. And so every single star has a unique fingerprint. It's fascinating stuff. All right, what am I going to talk to you about next? Okay. We spoke about the Obama lines, if anyone remembers, and we spoke about the Doppler effect, and we pretty much stopped at the Doppler effect. So I think people remember what the Doppler effect is, right? So for example, you love a science, that's awesome. Just one? It's good to see you, my friend. You know what's funny? This guy, he does all this work and he wears earplugs. Get the picture? He doesn't like the sound. Why should I have to... Anyway. So if I was to drive really fast away from this guy, it would go... Right? You know? And that's because by driving away from the sound, you are stretching out the wavelength of the sound. And so to us, in our brains, it sounds like a drop in pitch. Right? And I said pitch. Now with stars, as we know, this happens. In fact, it happens between Mercury and Earth, right? So, Mercury relative to Earth at its fastest relative to us is 30 miles per second, right? And that is enough to shift a microwave wavelength. So if you guys, let's say one of you was on Mercury and you turned on a microwave, does it make a sound and can we hear it? Ooh, that's a good question. It does not make a sound necessarily, because sound requires an atmosphere. If there's no atmosphere, there's no sound, right? And sound is basically just the compression and rebound of particles in the atmosphere that our brain has learned to interpret, right? That's all it is. So in space, when there's no atmosphere, you're not going to have a sound. Having said that, if you could survive being within the explosion, then the rush of particles might cause something that you could hear, but you'd be fried to bits. All right, next thing we were talking about. Yes, so Mercury, right? If you turn on a microwave in Mercury, right, that wave, the wave might be 8 inches long. I know I keep coming back to this. Might be 8 inches long, right? But that wave, if it reached Earth, would be 8.1 inches long. If Mercury is moving away from us at 30 miles per second, how one can attenuate light absorbed interstellar H2 when measuring atomic absorption in stars? How can one attenuate light absorbed? Is that what you mean to say? How can one attenuate light absorbed interstellar hydrogen when measuring atomic absorption in stars? Sorry, I typed too fast. It's all right. Your brain's going faster than your hands. I think most of us know the feeling. All right. So I spoke about the Doppler effect, and I spoke about Blackbody laws of radiation, and the Doppler effect here. Did you see Neil deGrasse? Do you mean Neil deGrasse Tyson? He had a new thing on YouTube which came out when he toured Australia. Nah, I tend not to visit people in person, but I did see him on YouTube afterwards with the guy from Spacetime, which was pretty fun. But it's good. He's at the moment he's repeating a lot of stuff for general people that he said before, which is great. It's good stuff. It's beautiful. Yeah. Okay, so the Obama alpha lines, and this is in response, I guess, partially to Abyss as well about attenuating hydrogen. It's through the reading of Balmer lines. So Balmer lines are formed by a mathematical equation, which has another relation called the Rydberg constant, which we won't get into in this lecture at the moment anyway. And these have specific lines that can only exist. I seriously believe Tesla was onto something big. Oh yeah, yeah, of course. They all are. They all are the geniuses in history. They mathematically emit lines at certain locations away from the nucleus. Okay, and that's because the electrons can only exist in our world. We live in a pixelated universe, as we all know, right? So the electrons can only exist. Can interstellar hydrogen absorb blackbody radiation from stars? Ooh, that's a good question. I would suggest that it depends on how far away, but absolutely, yes, absolutely. So it is important when you're making the measurements from here as to the content of the hydrogen between the thing you're measuring and us, because absolutely that's going to skew your measurements. Yes, that's exactly right. And how does one do that? Well, what happens is you know, as you probably already know the answer, you have to measure these stars over time throughout their orbits so that you can get the measurements from when they pass through different gases to when they're outside of the gases. Then you've got to get measurements of other things that have that gas. Yeah, no, perfect. All right. So the next, let's assume, right? Let's assume that, for example, I'll give you an example of how it's done. Let's say you go to the park. I don't know if you have parks in the US where you can put a kid on that spinning thing and they just go around and around and around. I don't know. They're not merry-go-rounds. They're like a little one at the park. They got rid of them in Australia because they were too dangerous, supposedly. Which is sort of funny because my cousin flew off one once and it was actually really funny. Anyway, right? What you can do, basically, what the scientists are doing, is that if you can't physically, the person at Tutang Frank, hey man, people are so far away, right, on this roundabout thing, the stars are so far away, that what you have to do is you've got to listen by looking at the redshift, right, the color change. And the color change is the same as if there was a kid on that, what up, talking about stars, and we don't have them either. Oh, there you go. So, you know, like, I'm trying to think of one. Well, if you put someone on one of those things, right, and someone goes, oh, you know, you hear them go, you know, so you close your eyes and you can hear roughly where they are because of the sound change, and that's what's happening with the stars. So the astronomers, instead of with sound, they do that with light. So as the light changes from blue to red, they figure out the orbit of the star, which is freaking awesome. All right, now let's talk about optical telescopes, the Doppler effect. Exactly, my friend, exactly. Optical telescopes. Okay. So, what is the point of the telescope? You need to have a really, really large telescope to get a lot of light. But what's awesome is that now, thanks to artificial intelligence, this is another thing, you know, we think that our jobs are going to go, hey, Boss Briggs, we think our jobs are going to go to robots. No. All of our jobs are going to go to robots. Even scientists are already losing their jobs to robots, right? Because artificial intelligence is now learning how to build better telescopes, how to position mini telescopes, a microwave on Mercury, was saying that when it moves away from us at 30 miles per second, the wavelength of the microwave changes from 8 inches to 8.001 inches or something like that, roughly, which is pretty cool. And that's how you can tell the orbit of Mercury. So you could basically, if you had a microwave on Mercury and I had the equipment to detect it, I could tell the speed of Mercury by doing that, by measuring the difference in wavelength. I'd have to use the same brand microwave. All right. So here's another interesting thing. We as humans have to use one telescope as humans because we have one brain, right? So we have to look at the telescope so that we can look at it into our brain. But now with artificial intelligence, what they can do is they can synchronize. This part is really cool. They can synchronize telescopes from across the globe into a virtual massive telescope, right? And the artificial intelligence is learning every weekend. Artificial intelligence learns what one scientist learns in 20,000 years, right? If anyone can imagine that. Yeah. Now it's different in different scopes. Like I've seen this happen before. Like, you know, you see it in Texas Texas Hold'em poker. We saw that over one weekend, the computer went from being the worst poker player. Neural network. Yeah, that's right, neural network. This artificial intelligence, this AI, went in one weekend from being the worst poker player in the world to beating the best poker players in the world. And it didn't beat just one, it beat them as a group, units. But human touch still needed, like Tabby Star. Fast learner. Yeah, well, yes, you're both 100% correct. You still need the human touch, but we don't know how long that's going to keep going for. But it is fascinating about how many people they're replacing. When I was at the nuclear science facility on my cursed scholarship, in every single room, in the labs, right, in the actual labs, there were robots that now replaced. They were not artificial intelligence, they were just dumbass robots, right? I will touch myself, that's great, I'm very happy for you. Every scientist had at least one robot who was doing half of the work for them in measuring all of the chemical compounds and McDuda and the analysis of the chemical constructs that came out from reactions. What do we do without jobs? Well, they're already talking about it, and that's, I think, one of the presidential running topics for Zuckerberg when he runs for president in 4 or 8 years, where he wants to propose a universal base income, which I don't want to get into now. Farm. Yeah, well, everyone will have their own AIs that can do the farming better than them too. Yeah. DNN is the future? DNN. You probably, I don't actually know, I'm not familiar with that acronym, I'm sorry. The future of humanity. Well, the future of humanity is already, you know, changing because we are, the deep neural network, sorry. Yes, the deep neural network. DNN just sounded like a dumber version of CNN. I'm like, fake news is when dumb. Anyway, nothing new. Do you like automated cars? Do I like them? That's a good question. I guess the best way to answer you is like this. If I was a horse rider, would I like automobiles? So you've got your own bias and you've got the objective bias. Let me answer you this way. On Friday nights, Saturday nights, you know, you don't have to worry, or wherever you go, you never have to drive. You can sit there, you can drink, you can do your study, you can talk to your friends. So these are all, you know, I guess like a cushy saddle. It's like a cushy saddle. Yeah. And the other thing is, every weekend in Australia, I don't know, I mean, I'm sure this is the same in America a million times over, but in Australia, every weekend, every Tesla that we have in Australia teaches every other Tesla of all of the potholes, all of the speed humps. I think humans are already no longer thinking for themselves to a very large degree, which is why we see a lot of stupidity possibly around. Yeah, we're going way off topic. Yeah, we're going way. I might have to delay these topics. This is more for the Gabsmack channel. I agree. Yeah. In the hands of government corrupt people isn't a positive to me. Yeah, we're definitely going off topic. All of these points are definitely valid to discuss. But it's like everything. I mean, we're talking to each other through Periscope, right? So already, no, don't be silly. It's not your fault. I get carried away as well because they're fun topics. But we're talking through Periscope now. Tell me how we would do this without, this technology. So we're already integrating with technology. Starlight, Starbright. Where's the damn owl? The owl will be coming to Gabsmack later, and there's a new character coming soon called Auntie May. I'll introduce you all to later. All right, refracting and reflecting telescopes, which we spoke about in the last lecture. And we spoke about the differences between them. And what we were doing is we were talking about how artificial intelligence is uniting telescopes around the world to learn how to see infinitely further. All right, powers of a telescope. Magnifying power. Here we go. Here's a new formula for you. Okay. Resolving power. Okay. Light gathering power is related to the area, which is pi r squared, so the radius squared of the telescope. We've already said that. And you can maximize that area, as we said, through AI combining things. Resolving power. Wave nature of light. The telescope aperture produces fringe rings that set a limit to the resolution of the telescope. Resolving power is a minimum angular distance between two objects that can be separated. For optical wavelengths, this gives 11.6 arc seconds. That's actually pretty insane. What the hell is that not? So basically, yeah, I know, it's so annoying. I'm so sorry, it's so annoying. Oh, anyway. We're supposed to live in this quiet street. It's the noisiest sawing up bones. That could be what he's doing. You never know. It's, I'll show you. Can you see him? Some guy sanding the ground or something. He's been doing it like for weeks. I'm like, what are you still sanding, man? Alright. So, here's an interesting... Hey, at least you'll be tanned. Right. So the minimum distance between two objects that can be separated. Right? The minimum distance is 1.22 times the wavelength divided by the distance between those two objects. So if you have two stars you're trying to look at, right? You got to look at the wavelength coming to you from the stars, and you got to look at the distance between those stars. Right? And 1.22 times the wavelength. Well, wavelengths are in a billionth of a meter. Up and down. A billionth of a meter, right? So basically 1.22 multiplied by a billionth of a meter, or however big the wavelength is, could be 100 billionths of a meter, 600 billionths of a meter, right? And divided by the distance between the stars. So if the distance between the stars is like, 100 kilometers, yeah, forget it. It's not going to happen. Okay. So magnifying power. Magnifying power is different to resolving power. Resolving power is the ability to see two separate objects as two separate objects. Okay? So that's part of our test. That will be tested later. The next one is magnifying power. Magnifying power is probably easier. That's the ability for something to make it bigger. Okay? And that is not a dirty joke. Let us move on. Okay, so we want the ratio of the focal length of the primary mirror, right, over the lens and the eyepiece. Eye distance in triangle. Yes, that's exactly right, my friend. Well done. Exactly right. All right. Far away from civilization. is where you want to have a telescope. Best location for a telescope. All right, here we go. This is the Paranal Observatory in Chile, which actually spelled like Paranal. Paranal Observatory in Chile, on high mountaintops to avoid atmospheric turbulence, seeing and other weather effects. Okay, traditional telescopes. The 4-meter Mayol telescope at Kitt Peak National Observatory in Arizona. Okay, that's good. There you go. So traditional telescopes are in Arizona. Arizona has something traditional. Advances in modern telescope design. This is amazing. This is some of the things that humans and computers together came up with, right? And they are dynamically controlled by computers, right? You can have a segmented mirror. If you have a segmented mirror, right, then it's like a bee eye. That's crazy. It's crazy that humans and computers together are now designing bee eyes to be able to see stuff. Have a look at this. This is crazy. Are you leaving up replay? You can see all the replays from Gabflix if you subscribe to Gabflix, or I think I do leave the replays here too. In Chile, I used to look into Center Milky Way. Yes, they are. Okay, so here we go. All right, here is a floppy mirror. Hey, no worries. I think if you click on the link in the description, you can get access to the site, and all my channels are there together. You're always welcome. That's what we're here for, my friend. So here is an original style mirror, and you can see because it's so big, it's going to be so heavy, so massive. And because it's so heavy, you need really strong support. So it's really expensive. That's the one. Paint Something is one of our first members, actually. All right, so you got to do this, and you can see that this wobbles, right? Because it's like a trampoline. This mirror is basically a trampoline, right, in terms of the weather structure. But look what they designed. Look at that. That's like a bee eye. They've got hundreds of mini mirrors, all shaped hexagonally, right? And the computer then translates all of this into one image. That is insane. Insane. You know, Isaac Newton, who developed optics, would never have been able to do that with his technology. So it's just crazy, because that way what you do is you have hundreds of mini eyes, and then you don't need all of the massive support, because each one is able to be sustained separately. You know, if one breaks, you can put another one in. You know, if one's not done properly. With the other floppy mirror, you have to have it perfect, absolutely perfect on every edge, and if there's one scratch, it's all over. Like the old DVDs or CDs from the old days, if anyone remembers those. All right, modern telescope. Okay, so now with new computers, they're all controlled by computers now. With new computers, with new telescopes, VHS. with new telescopes, they're all controlled by computers, which is insane, because a computer can move something, right, to you know, a thousands and thousandths of a degree compared to what humans can move. Because our eyes and brains and muscles and all of that together, right, we can move like this. Those things can move so small that we can't even see them as humans, that they've actually moved, right? So it's just phenomenal what computers can do these days. Transformation, yes. All right. So examples of modern designs, we've already gone through that. All right. Now we're going to get on to radio astronomy. All right. Why is radio astronomy important? Because humans are blind. They shoot laser to measure atmospheric refraction and adjust the mini mirrors accordingly. That is exactly correct. That's exactly correct. I'm going to watch replays. Oh, anytime, Lulu. Anytime. Radio astronomy, right? First of all, right, the radio wavelengths are longer. And because they're longer, they get through the atmosphere, right? Quite easily. Unlike something like a gamma ray or something that's deliberately, you know, our atmosphere has evolved to block that out. Okay. And it just goes to show you how blind we are as humans. What makes radio astronomy any less valid than using visual light? The only difference is because we as humans can only see visual light, right? So these things are like extra eyes, you know, that humans don't have, and you can see so much more through radio waves. And what's really cool is that computers convert the radio waves into visual waves. right? Because they just modulate them upwards into the visual spectrum, and so you can see things you could never have seen otherwise. Okay. Amplified signals are stored in computers and converted into images and spectra, right? Which is pretty cool because they can use amplifiers. Lady Raincorn, how you going, Sab Sab? Long time. Okay. Here is a radio telescope, which is 1/5 of a mile in Puerto Rico. All right. And then in West Virginia, there is a 0.16 of a mile telescope. But the one in Puerto Rico, right? 1/5 of a freaking mile through radio waves, no obstruction from cosmic dust. Again, exactly. Abyss is awesome. He's like my technical translator. I'll say it in some dodgy English version and he'll bring it out. Hello, Sab Sab. All right. You can almost see it from space, man. This 300-meter telescope in Arecibo, Puerto Rico. All right. Observing beyond the ends of the visible spectrum. So, here we've got the NASA infrared telescope on Mauna Kea in Hawaii. Okay. We've got infrared cameras need to be cooled to very low temperatures, usually via liquid nitrogen, which you're talking like hundreds of degrees below zero, right? However, from high mountaintops or high flying airplanes, some infrared radiation can still be observed. Pretty cool. The problem you have, and Abyss will know this as well, is that when you have a shorter wavelength, they tend to get scattered more easily. In West Virginia, prohibit any radio devices within more than 50 miles. Wow, 50 miles. That's crazy. That just shows you how powerful they are. Alrighty, and now we move on to the ultimate telescope that everyone knows. The Hubble Space Telescope. What does the cold do? It allows the cameras to operate, otherwise they're unable to detect the infrared. And I think that's because infrared is heat. And so because they're sensitive to heat, they have to be very, very, very cold compared to the heat itself so that they can actually see it. Avoids turbulence in the Earth's atmosphere. Launched in 1990, maintained and upgraded by several Space Shuttle service missions throughout the 90s and 2000s. Edwin Hubble, another brilliant person who discovered that there were things that existed outside of the Milky Way. Before that, we used to think that the Milky Way was everything. He also showed us that the universe was expanding. And which is funny because Einstein proved that mathematically years before. The meteor showers from yesterday. No, unfortunately. These are things you could scope, my friend. That would be amazing. Avoids turbulence in the Earth's atmosphere and extends imaging and spectroscopy to invisible, infrared, and ultraviolet. Ultraviolet spectroscopy, which is amazing because now, right, these are fingerprints that our eyes couldn't even see on both sides. Talk about both sides, right? Both sides of the spectrum. No pun intended. Almost, we're in the last quarter now. Ultraviolet rays, absolutely. Right? We picked them up as humans. We picked them up in getting a tan, basically. All right, infrared astronomy from orbit. All right, who here has heard of the NASA Spitzer space telescope? Okay, so half. Cool. Well, the Spitzer one looks at something called far infrared. Okay, and far infrared, right? It has very long wavelengths, very long. In fact, they're much longer than infrared waves that make it to the Earth. And the fact that astronomers TV control much longer than TV control, yeah, much longer. They don't have that much energy content, and so it's very hard for them to make it through into the Earth as well. And they're fascinating because how did astronomers even know that they existed? Right? Through mathematics, they knew that there was a gap missing in the spectrum of electromagnetic radiation. Right? We go all the way up from gamma X-rays all the way down to to radio waves and stuff. And we're like, hold on, there's something missing here. And they've realized that there must be this thing called far infrared. How they were able to do that, and they had the confidence to do it, and then they had the proposal to go to NASA and say, give us millions of dollars to put this thing into space, the Spitzer, because we think it exists, right? Talk about confidence, and it worked. It's just quite fascinating. All right, now we're going to talk about CCD imaging, which is charged couple device. God's dead, hey. All right. Now, charge coupled devices. Okay, so it's like dark matter. I guess so. It would have been the dark matter of the old days. Yeah, that's right. So with the charge coupled device, right? Basically, it's able to pick up differences in charge, and that is actually even more sensitive than a photographic plate. No one thought it existed. The new James Webb Telescope will detect in microwave and radio ranges no UV. It's amazing all the different telescopes now that are being designed. And I was watching this thing on TED where the new computers, the AI actually goes through hundreds of thousands of potential designs before a human can even do 1% of it. And so by the end of a few hours, it's been able to come up with a design based upon set parameters that a human would take years to design. I'm not kidding, years. It's able to do in hours. It's just phenomenal, man. It does all of the mathematical wind testing, the wind tunneling. So future cars will be all designed like that too. So in other words, architects, engineers, yeah, they'll all lose their jobs. You won't be able to do anything without the AI. Anyway, so charge coupled imaging through charge coupled devices. Charge coupled devices, is that about drone design? Ah, you saw that. Yeah, that's right. That's exactly right, my friend. I guess I know what you do in your spare time. So, yeah. If anyone notices at night with your phone, every time I learn a new way, that's awesome. Thanks, Boss Briggs. That means a lot. With your phones at night, you notice you see this amazing stars and this amazing party, and you want to get a photo of everyone, and you take a photo and you just lose 90% of it in the club or at the restaurant or wherever you are. So if your phone had CCD imaging, right, which it wouldn't, closer to Gene Roddenberry's world, we are, my friend. We're getting closer and closer. All right. So this stuff can write straight onto computers. Right? You don't need to have photosensitivity. That camera's a skater. They are pretty damn shit. All right, so here we are now with the spectrograph. Okay, the spectrograph is important to split up the light that comes to us. Why is it important to split it up? Because once you split it up, you're able to see the fingerprint of the light. You can see how much of it came in that was blue, how much that was red, exactly which shade of red, the intensity, the lines within it, right? So all of that tells you everything about the star. Because as we said, we live in a pixelated universe and we take advantage of that. So number one, a pixelated universe means that we're not really real in the way that we think we are. Yeah, no blur. We're all sort of like, we're just like high resolution forms of something.
All day like this, all night, 7 days a week.
Yeah, I'm teaching.
When I want to help nobody. All right, no worries.
You want to help me with my uni?
Okay.
We live in a pixelated universe. We do. And in fact, I might talk about that in another lecture on the holographic universe, high-res pixels, yes. And the size of the size of the pixels is the Planck constant, right? So we're talking like a millionth, a thousandth of a millionth of a billionth of a billionth. You love his little voice. Yeah, he's a cutie. Had a big of coffee. Yeah, I haven't had any today. I'm pissed off. I want to have some. It's all right. We'll have some for lunch. Alrighty. So, because they sent New Horizon Telescope to do a flyby and take a picture. Abyss, man, we got to do a joint scope one day. Seriously, I shit you not. This is one of the beautiful things about Periscope is that all these brains everywhere combine. You got to take a coffee break, yeah. Adaptive optics. All right, so this is the crazy one. Adaptive optics. The computer-controlled mirrors, right, that we were just talking about before. They adjust the mirror surface many times per second. Man, if you message me on Facebook, on it's called Gabsmacked, and or just send a tweet to Gabversity, and we'll share our Skype details, and we'll do a scope. Adjust the mirror surface many times per second to compensate for distortions by atmospheric turbulence. Now that's insane, because even on the most perfect of evenings, and your brain, my brain, can't sense anything. It's just dead perfect on the top of some mountain, almost no atmosphere. Even then, the computer can pick up enough atmospheric turbulence to make a shift with the telescope tens and tens of times per second. Per second, right? It's just ridiculous. So it just shows you how we have already integrated with computers, whether we like it or not. You tell me how long you can spend away from your phone. You know, we are sort of retarded compared to, you know, a more advanced version of ourselves. Like the sound of planets, damn straight. All right. Interferometry is the next thing, and we're almost done with this lecture. Okay? Interferometry, okay? The resolving power of a telescope depends on the diameter, if you remember. Okay? So we have the diameter of the telescope, and we have 1.22 times the wavelength that's coming in. I think I said diameter between the stars. I meant to say diameter between telescope, but it's the same thing, right? Because the telescope relative to the stars have to fight for information. Yeah, that's true. That's true. And you know, we have now augmented our memory capacity, right? Because if there's something you don't remember, you just go into your phone right there and then. I remember once I was teaching Italian or French, I can't remember. And there was a question, there was a word I didn't know, so I walked behind the blackboard, quickly looked it up in Google Translate, and walked back out. I'm like, okay. All right. And exactly what I was saying, the combination of several smaller telescopes into one big mirror is interferometry. All right? So basically, it's the study of interference patterns. That stuff is phenomenal, right? And we do that a lot in quantum mechanics as well, where you've got to track all of the waves and then combine them into a big wave mathematically, and that mathematical superposition wave, I recommend you who studies cosmology and telescopes. Oh, awesome. Cool bananas. All right. So, has a unique sound, even the sun. Yeah, absolutely. This is very true, yeah. Yeah. So we have here that the interference pattern is generated in a computer. It's not even happening in real life. Yep. And that computer created superpositioned wave is actually what we would see if we had a telescope big enough. So what's amazing is that the computer can make an image that's not even there. So the question is the image really there? Right? Or is it only there because we recreated it with a computer? And what does that tell you about the reality of images? You know, we live in a world where we interact with things, and that's what makes it real. Is it still real when we're not interacting with it? Quantum mechanics tells us it's not. It's only real when you interact with it. Apart from that, it's something deeper that we don't yet understand. Something to do with fields, interactions between fields. Okay. Now, what I'm going to show you, the second last thing I'm going to show you, is a radio map. All right, have a look at this. So you would never see this at all. None of us would see this as a human, right? But through integrating ourselves with computers, can you observe something without affecting it? No, correct. You cannot. Not yet, anyway. Quantum physics. So this here would be completely invisible to us. What color code? Yeah, you can't see this, but this is actually a difference in intensity. So there are more radio waves in the center than on the outside. And so whatever that they're looking at here, which doesn't say, it shows, now how do we extract free energy from the ether? I think we have to extract it from the sun first. The heat has color. Yes, well, it's translated into colors. Right? It's translated into colors for our human brain. Is red. Yeah, the more intense is more red. Yeah. So, but and then the more intense is more blue. So what they do is they push it up with a computer. They modulate the spectra, right? So modulating a spectra is like, you know, when you play someone's voice in fast forward, and their voice goes from this to, you know what I mean? That's what they're doing with radio waves. You push them up into the visual, so you can see them. But that's basically a compressed version, if you want to call it that, right? But it's not the true color. No, because, see, that's the other thing. Color only exists in the human brain. The color is not actually out there, right? That's the interesting thing. Yeah, it's not real. Yeah, you're 100% right, yeah. Even color is not real. Color is just what our brains naturally see, yeah. Well, and Marley would know, you know, with being in IT, he would be working with codes all the time and, you know, taking code and turning it into something you can see. So that's exactly what's going on, right? Okay. So we have a problem with radio waves. Here is the difference. With light waves, because they're so short, right? Because light waves are so short, it's easy to see the distance between two stars that are sort of close to each other. Because there's a small site in the vast EMs. Exactly. Is the same blue as you see? That's a very good question. You actually don't know. No one knows, right? We just think it's probably true because when you sample nodes in human brains, the color receptor nodes, right? They are built the same for roughly for every human that's had their eye examined after they were dead, right? Or if they had an eye removed, then you look at the nodes, right? They all look the same. We think we see blue. So, but you're right, absolutely right. I actually think men and women see color differently, but that's because men and women on average have a different nodal structure in the eye. So with radio waves, because they're so long, right, it's very hard to see neighboring stars. So what you have to do is normally you would have to have a radio telescope. You'd have to have it the size of the Earth, right, basically to keep up with a smaller sized light telescope. Well, what do we do in the age of computers? Well, we get a telescope on one side of the US, a radio telescope, another telescope on the other side of the US, and then those two separate pieces of information get joined by a computer in some server somewhere else in the US or even in India or whatever now, right? And that's how it happens. So it goes to show you that we've already left humanity. We're already partially integrated with computers. So I see the future as more and more of an integration with computers, which will be a difficult thing to do because those who are truck drivers, those who are entry-level scientists, those who are architects, those who are car designers, they're all going to lose their jobs. So we'll talk about that, I guess, in another scope. All right, so I'm going to show you, right, here is, I don't know where this is. I think, oh yeah, this is over the entire US. This is crazy. This goes to show you, right, why Americans need to look back and be proud of what they did back in the days in the 50s, 60s, 70s, right? And it's bigger than, you know, it's bigger than emotions, and these are the things that we as in the West need to aspire to, right? We need to aspire to this beautiful advancement of humanity which can help make lives better for everyone around the world, right? Have a look at this. This is insane. This is what Americans built years ago, back when they still, you know, were able to, you know, do things quite well, right? That is an array of telescopes. Each one of those telescopes is delivering a continuous feed of radio particles, right? The 70s. A continuous feed of radio waves by hundreds and hundreds and hundreds of these things. Let's build more on the fast side. I love your thinking, my friend. That's exactly what we need to be doing. We need to start building them on the moon and freaking on every other damn planet, you know? Get out of here. Anyway, and each one of those through a massive, massive, massive computer network, right? Not yet the DNN, but pretty soon, right? All of them, and in orbit, absolutely. Yeah, all of them get fed into one large wave. You're talking billions and billions and billions of datum, right? Of bits of data, or bits of datum, right? Billions, right? You're talking per minute. The brain power that's required to get this technology, right? And now they also use it. They also use it to track weather patterns. Yep. They use it to track weather patterns in the US, especially in the US more than other places, to figure out, you know, the snowstorms and things that are coming that can't be seen with natural light. Okay. The last thing, right? The last thing we're going to talk about is, and this is only going to be quick, is cosmic rays. Cosmic rays, right, are also electromagnetic radiation. And Earth is constantly bombarded with and by highly energetic subatomic particles from space. This is very, very interesting to me in studying quantum mechanics, because there is actually not enough time for these particles to reach the Earth, because they don't live long enough, and yet they still make it. And the reason, one of the reasons they make it, is because they are traveling so fast that time for them shrinks. So they're traveling into our future, right? So they might only live for a fraction of a second, but for us, they live for a few seconds. Warp speed. They're traveling at warp speed. That's right. That's exactly right. And until today, no one knows the exact source of all cosmic rays. No one knows. Because there's a new hypothesis that I've been working on in quantum mechanics, which I've always thought, and I think some people here thought as well, but there are a lot of quantum particles that travel backwards in time, or they travel sideways in time, or they travel on an angle compared to time. Can we time travel? We time travel all the time. On Earth, time travels a bit more into the future than in space. Yeah, they travel at 99.99996 roughly the speed of light. So, you know, like a fraction of a second for them could be many seconds for us. It's quite fascinating. Anyway, so yeah, the quant, and that's why, can we go into the past? No. But wouldn't that make them antimatter? That is, actually, you and I were talking about that last time, where something traveling 100% in the direction of our past is also consistent with being antimatter. Yes. Travel the speed of darkness. Yeah, well, nothing travels the speed of darkness except light. And light travels at the speed of causality. And causality is the speed at which things happen. All right? Because we live in a fluid. We live in some sort of weird-ass fluid where if something happens here, that happening has to travel, right? Be parallel to its spectral equivalents. Not necessarily. Not necessarily. I think light is a little slower. That's interesting. I haven't seen that, but I'll look that up. But that's another good, interesting point. I don't think that might be true with refracted light, relative to us. But I think the photons themselves travel at the speed of causality, or bent light. Yeah. Well, see, what happens is that when you bend the light and slow it down, time slows down with it. So there is something around the fabric of our universe, right, that allows light to travel through it at the speed that fabric occurs. There are lots of anomalies in the universe. Superluminous mass ejection from quasars, absolutely. Darkness always beats. Black holes bend light. Black holes don't bend light directly. They bend the space-time. They bend our four-dimensional fabric in which we live. And light, as a part of that fabric itself, it seems to be a property of the fabric somehow, light. And so when you bend the fabric, you bend the light. All right, well, that's the end of our astronomy lecture. We've still got another 8 or 9 before the exams. Has a website you might like, Radio Astronomy. You should share it with us, man. Just share it on Gabversity so that other people can learn as well. It's great, man. Honestly, what do we have collectively? You know, our minds together, our IQ goes through the roof, and we can, fingers crossed, help learn more and more and help make the world a better place. Until next time, I'm going to do some quantum mechanics later today on Gabversity. for those who are mathematically inclined. For the rest of you, always a pleasure to see you. And remember, at Gabversity, facts don't care about your feelings. Likewise. Okay. Dennis Makes. Awesome.